All right, today we are diving deep into the heart of our very own star. We're going to talk about how a brand new algorithm, one that's actually inspired by evolution, has just cracked a puzzle that's had scientists scratching their heads for centuries. Let's get into it.
That sounds like something straight out of science fiction, right? How on earth could we possibly figure out what's happening deep inside the sun? It's a place we can never, ever directly see. And that, right there, is the massive challenge at the center of this whole story.
For 3 full centuries, we've been watching the sun. We've seen its face break out in these dark spots and then clear up again, almost like clockwork, every 11 years. So we have this amazing, super detailed record of what it does, but the actual engine driving that rhythm, it's completely hidden from us.
So let's start with that heartbeat. This isn't just some, academic thing scientists like to ponder. Understanding this solar cycle is absolutely critical. Its ups and downs can mess with everything from our power grids and satellites to our planet's climate. It's truly one of the biggest puzzles in astrophysics. And here's the key thing to remember. Those sunspots we see, they're just the symptoms on the surface. The real cause is this gigantic magnetic engine, they call it a dynamo, that's just churning away deep inside the sun. So if we can't look inside to see it, what's the next best thing?
Well, since we can't exactly send a probe into the sun, scientists have to do the next best thing. They have to build a virtual one. So let's take a look at the main tool they use to try and understand this hidden process.
It's called a flux transport dynamo model. The easiest way to think about it is like a super complex weather forecasting model, but instead of predicting rain, it's predicting the physics of a star. It runs on massive supercomputers, and it follows all the fundamental rules of how plasma flows and how magnetic fields get cooked up inside our sun.
And this is so cool. This shows you exactly what those simulations spit out. It's called a butterfly diagram. See how it shows the magnetic activity popping up in the middle latitudes and then drifting down toward the equator over that 11-year cycle? It creates this classic wing shape, which is exactly what we see when we observe the real sun.
Okay, but here's the catch. For decades, these amazing simulations have hit a massive wall. It's basically a problem of getting all the settings, all the little dials, turned to just the right position.
And this quote from the research paper really gets to the heart of it. Scientists are basically working in the dark. Because we can't see what's happening deep inside the sun, a lot of the most important numbers you need to plug into the simulation have to be guessed.
This chart lays out the problem perfectly. On the left, you've got things we know for sure, like the sun's size and how fast it spins. But on the right are the unknowns, the really critical stuff, like how fast plasma is flowing deep down or how strong the magnetic field generation is. Trying to find the right combination of those unknowns by hand, it's like trying to open a safe that has millions and millions of dials. It's basically impossible.
So, how in the world do you solve an impossible tuning problem? Well, you don't do it by hand. You get an AI to do it for you. And you use one of the most powerful processes in the entire universe as your guide: evolution.
This, right here, is the brilliant idea. A genetic algorithm doesn't just try one combination of settings at a time. No, it creates a whole population of virtual suns, and each one has a different genetic code for all those unknown settings. Then, it tests them all, sees which ones look the most like our real sun, and then breeds them to create a new and hopefully better generation.
This little flowchart shows you exactly how it works. You start with a whole generation of simulations. You run them, you grade them, you pick the best ones, and they become the parents for the next generation. It's literally survival of the fittest, but for computer models of a star. How cool is that?
So let's just break it down real quick. Step 1. You create a population of, say, 30 random models. Step 2. You test their fitness by seeing how well their sunspot cycles match up against our 300-year historical record. Step 3. The best ones, the ones that match the closest, get selected to breed. And then step 4, which is really clever, you introduce tiny random changes, mutations, to keep exploring new possibilities. And then you just repeat the whole cycle over and over and over again, getting closer to the perfect answer with every single generation.
Okay, so after all these generations of evolving the perfect solar simulation, what did they actually find? This is where things get really, really exciting.
Did this AI actually pull it off? Did it manage to reverse engineer our star and finally crack the code of its hidden physics?
Oh, yes. Yes, it did. Just look at this graph. The red line is the real, observed number of sunspots over the last 300 years. The blue line is what the algorithm's final, super-evolved simulation came up with. The match is it's stunning. It recreated everything, from the normal cycles to those weird historical quiet periods, like the Dalton Minimum back in the early 1800s.
And here's the number that proves it, a correlation coefficient of 0.876. Now, in statistics, a perfect one-to-one match is 1. So this is incredibly close. It just shows that the model captured the sun's history with just remarkable accuracy.
But here's the real scientific breakthrough. The model didn't just play back a recording of history. By figuring out the correct physics, it actually uncovered a hidden relationship inside the sun's engine, something that scientists had theorized about for years, but could never quite prove.
And this led to a huge discovery. Basically, the sun has a memory. The algorithm confirmed that the strength of the magnetic field up at the sun's poles at the end of one cycle is an incredibly strong predictor of how many sunspots are going to show up in the next cycle, about 11 years later.
And look at the correlation here. It's even stronger, 0.916. This relationship is one of the absolute most important keys to understanding and maybe, just maybe, one day predicting the strength of future solar cycles.
So let's just quickly sum up the big takeaways here. First, an AI that mimics evolution can actually reverse engineer the hidden physics of a star, which is just mind-blowing. In doing that, it perfectly recreated 3 centuries of the sun's history, and maybe most importantly, it proved that this powerful memory effect exists, where one cycle sets the stage for the next one.
And the researchers, they are not stopping here. As they say in this quote, they think this same method can be used with even older data, things like isotope data from tree rings or ice cores, or even ancient historical documents, to push our understanding of the sun's behavior even further back in time.
And this, of course, brings us to the final fascinating question. This whole breakthrough was about looking backward, about recreating the past. But by proving that we can understand the sun's hidden engine with this much accuracy, it opens the door to an absolutely tantalizing possibility. A future where we can finally and reliably predict what our star is going to do next.